Hi everyone, this video is going to be all about reference table H. So if you have your reference tables with you, take a look at table H as you're watching this video so you can follow along easily. All right, so looking at table H, what I really just see is one big old graph, and that graph is relating temperature to vapor pressure. And as any fourth grader could tell you, since all four of these lines go up, that must mean that as I increase the temperature, the vapor pressure also increases. Great. What that tells me is that as molecules gain more kinetic energy, they have more ability to move and to move faster, so more are able to break free and sit as gases above their respective liquids, like we talked about in the previous video on vapor pressure. So table H just records that process for 4 different liquids that the Regents people have deemed as important. So there's lots of information that we can pull from this graph. Let's take a look at some of it. The first thing that sticks out to me is this line that has been drawn right here at 101.3 kPa. If you're keen to your reference tables, you've seen this number on reference table A, and it refers to standard pressure. And the reason that this line has been drawn in right on table H is because pressure is related to boiling point. And for the most part, we're working with systems that are sitting at standard or normal pressure. And so when we see the point where this standard pressure line intersects with all 4 of these liquids, the respective temperatures associated with those intersections are referred to as the normal boiling points. All that means is the temperature at which the liquid boils when the pressure is 101.3 kPa. So if we take a look at water and ask what water's normal boiling point is, I'm going to come across to 101.3 kPa, hit the water line, come right down, and here we are at 100 degrees Celsius. You guys knew that normally water will boil at 100 degrees Celsius. But what if circumstances change? Let's say you climb a mountain and the pressure of the air decreases. What that means is there's less pressure keeping the liquid sort of in its liquid state, so it's actually going to boil at a lower temperature. And we know from this graph exactly how much lower. Let's say we've cranked the atmospheric pressure down to, 70 kPa. That would put us about right here on the graph. Our y-axis goes in increments of 10, so be careful with that. Here we are at 70. If I want to know the temperature that water boils when the pressure is 70 kPa, I'm going to come all the way across until I hit my water curve, come down, and find that I'm sitting at about 91 degrees Celsius. Please be careful because the scale on the x-axis is by 5s. We're by 10s on this side and by 5s on this side. So this is a great reference table to write all over to make sure that your numbers on the scale are matching what you think that you're reading. So that information tells me that when I lower the pressure, I can actually decrease the temperature at which substances are able to boil. Pretty cool. Besides just this straight temperature, pressure, graph reading skill, we can start doing some comparisons using table H. So let's say I have all 4 of these liquids at 60 degrees Celsius. That puts me right here on my graph. If I shoot up from 60 degrees Celsius, I notice I run into the ethanoic acid line first, then the water line, then the ethanol line, and all the way up here, the propanone line. What that tells me is that at this particular temperature, ethanoic acid has a very low vapor pressure, whereas propanone has a much, much, much higher vapor pressure. If you think back to the links between vapor pressure and intermolecular forces, what that lets you know is it's much harder to change this liquid into a gas than it is to change this liquid into a gas. So looking at a particular temperature tells you the relative strength of intermolecular forces by checking out the relative vapor pressures at that particular temperature. The last thing I think you can really do with this particular reference table is kind of look across at a particular pressure. We started by looking at this standard pressure line, and you notice that all four liquids intersected that pressure line at different points. We look specifically at water, but we could compare this normal boiling point of water to, say, the normal boiling point of ethanol. And what we're going to notice is that if the pressure is 101.3 kPa, the temperature only has to get up to about 80 to boil ethanol, whereas we need to crank it up to 100 to boil the water. So again, we're seeing that same relationship we talked about in the last video on vapor pressure, that because of this difference in boiling points, we can draw conclusions again about the strength of the intermolecular forces holding these liquids together. Propanones must be quite weak because it boils at a low temperature. Ethanol's a little bit stronger, water stronger still, and ethanoic acids the absolute strongest. So using this table and sort of making the links between vapor pressure and temperature, we can do some direct readings or we can do some comparisons, but this table is chock full of information. You're just going to want to make sure you're reading it in the right way. Be careful with scale, be careful with this term normal, and you should be able to pull lots of success from Table H.